In the previous session, the field data recorded in the project was presented. Now we will introduce you to a use case that uses this field data. My name is Heuer from the DLR, and together with my colleague Pierre from PMSF, on behalf of Continental, we will present you the use case of data-driven sensor model validation.
We will first cover the overall ALKS use case, as well as the role of virtual validation, and then drill down into the data-driven sensor model validation approach, relevant data sources and formats, the methodology, and initial results. Finally, we will place the use case in the context of Gaia X and relevant challenges, and give an outlook of future development. The use case centers around the efficient development of an automated lane keeping system, ALKS. This is an autonomous driving system that doesn't require driver supervision on motorways. When activated, it allows the driver to do non-driving tasks until alerted otherwise. ALKS is governed by UNECE Regulation 157 and amounts to Level 3 vehicle automation. It is essentially a more robust combination of adaptive cruise control and lane centering assist. We want to develop and validate an ALKS function in the context of the overall vehicle system according to the criteria and scenarios set out in UNECE 157. To do this efficiently requires the use of virtual validation, employing simulation using virtual worlds to test and validate the ALKS function. To create a credible virtual validation approach, we need to validate the virtual world against the real world for the scenarios we want to test. In this presentation, we will focus on the sensor parts of the simulation, as this requires large amounts of data due to the wide variety of sensory inputs a sensor will encounter in reality, and the complexity of the metrics needed to characterize it. Where in the real world, the actual sensor interacts in myriad ways with the real environment, in the virtual world, this is replaced by a sensor model acting as a virtual sensor into the virtual environment provided by the environment simulation. To validate the performance of the virtual sensor, we perform numerous scenarios in the real world, recording both the actual sensor output and, using highly accurate reference sensors, also the actual environment in high resolution. This provides the ground truth data needed to replicate the environment in the virtual world. The same scenarios can now be performed using the sensor model in the virtual world while recording the virtual sensor output. By analyzing both real and virtual sensor output data and comparing them, we can calculate relevant key performance indicators and equivalence metrics, allowing us to then judge the validity of the sensor model as well as its limits of applicability.
After Pierre introduced you to the overall objectives and goals in our project, as well as to our use case, I will now go into the details of our methodology. As you heard in the previous presentations, we performed several test drives. One of these test drives were at the testbed Lower Saxony, where an object detection system collects data about all the traffic. So we design our test setup that we drive with our ego vehicle on this public motorway. This ego vehicle is equipped with a system under test, here the radar model, a radar sensor. The radar sensor is used to record the real physical detections of the sensor. This data is in a proprietary format, and in order to compare it later on, we need to convert it. So we perform a conversion step into the shared or common data format ASAM Open Simulation Interface. Now we want to replicate the scenario inside the simulation. So the simulation is constructed using two components. The first component is the simulation core or environment simulator, and the second component is the sensor model. This model tries to replicate the physical properties of the real sensor. So it tries to behave like a physical sensor would do in the simulation. And in order to simulate, we need the scenario data and the knowledge about how the scenario was performed. So we need the scenario. We construct the scenario using different data sources. The first data source is the ego vehicle data directly from the car. The second data source is the surrounding traffic provided by the infrastructure. And the third data source is from the weather station in order to provide environment information. These data sources build our inputs to the simulation. And now we can simulate and run the simulator and the sensor model. Now, a virtual sensor output is generated. This output is directly in the ASAM OC data format. Now we have two data sets. One is the reader sensor data, the second one is the virtual sensor data, both in the same data format. And then we can compare them directly against each other and perform our evaluation, calculate some metrics, and so on. So after you now know about the overall methodology, I will go into the details of the data formats and data sources. Previously, we introduced three data types. These were the physical sensor, the traffic environment, and the ego vehicle data. So our goal is to reproduce it in simulation and compare these data against each other. So we need a solution in order to have them in a common data format. Our solution is the standardized data format ASAM Open Simulation Interface. So we build converters, as you've already seen, to this data format. What is this data format about? ASAM Open Simulation Interface was introduced in order to couple simulators with other simulators or simulation components like sensor models or driving functions. How was the intended? So we have a simulation environment and we populate it using a scenario and also a map in order to create the simulation. And now the ASAM Open Simulation Interface comes into place in that terms that it enables standardized interface to talk to other components. As you can see in this following diagram, the environment simulator sends several messages to a sensor model. The sensor model then generates output, which could be input to an automated driving function, which then outputs information, for example, a motion request, to a dynamics model, which replicates the dynamics of physics, and which finally outputs some traffic update, how the simulation would behave in the next time step or steps. So for our use case, two of these messages are of particular interest. The first one is the sensor view, and the second one is the sensor data. Sensor view provides the input to the sensor model, and the sensor data provides the output of this model. The sensor view contains ground truth information from the simulator, what is really the current state, and the sensor model replicates or tries to imitate the behavior of the physical model in the simulation and generates a limited view in form of the sensor data. To get a more detailed insight into both of these data formats, I brought you a textual representation, a small excerpt of one of the collected data. On the left side, you see a textual representation of the sensor view message, and on the right side, one of the sensor data message. In general, there's input, for example, in the sensor view, general information like identifier of a detected object, and it's described with several properties like dimensions or position and also classification. So these general information, the structure is mostly the same between sensor view and sensor data. But what differs are the properties between those two messages. As you can see, the sensor model changes the dimensions of the detected object according to some functionality. as well as you can see the positions change. This is due to the sensor view is in a global coordinate system and the sensor data is in a relative positioning system. So after you know about this data format, we now need to get this data. Where do we get this data from? It is from the previous session. It is from the field data presentation. So as you can see, we have the vehicle data, infrastructure data, and many more sources. And now we can construct a simulation out of this setup or all of this data. So finally, we can now create our simulation replication of the real scenario. In the following videos, you will see the same situation in different visualizations of different data. It's the same source data, but it's visualized in different states. So in the center, you see a visualization of a simulation core. Here it's Scala. And on the top left and top right, you see the view of the infrastructure on the scenario. And on the bottom right, you see a visualization of the sensor model output. So the situation or the scenarios in every situation the same. It's a cut-in scenario you already seen in the field data session. So I play now the video and you can see the cut-in from the infrastructure perspective, how it's replicated into the Scala simulator, and finally on the bottom right, the output of the sensor model. As you can see, now the cut-in maneuver is performed, and on the bottom right, you can see the sensor has a limited view of the objects. So you see on the bottom right, there's a smaller excerpt of the bounding box than the physical object has in reality. So after we now simulated all of the scenarios and generated outputs, we can now evaluate the model. Our goal is to determine the limits and usable scopes under which a model is valid. So we know that every model has its specific purpose and it's built exactly for that purpose. And the challenge is to know if the model is valid for a specific purpose. So now we want to determine if it's valid for that purpose. As a result of the previous comparison, we had two data sets of the same situation. So we can compare each entity one by one. And here are some possible metrics and error distributions. We can compare both data sets against each other. Since we are at the halftime of this project, we did not fully evaluate sensor and sensor model. But we have limited or a preview of our evaluation already present. Here, for example, we will introduce you into the length error of the physical sensor. It's just a visualization of the error behavior of the physical sensor. So what you can see is on the y-axis is the length error in meter, and on the y-axis the time. So you can see that the error varies over time. What we can observe is that in the first place, the error is nearly constant, and in later time, the error varies over time. This makes sense with further information, since in the first place, both cars were at standstill, though the error does not really deviate. In the later place, both cars accelerate and the error deviates over time. So as we can see, there are certain behaviors of the sensor in different situations. And also what's interesting is if we analyze the error behavior in a specific part, it's, for example, normal distributed. So we evaluate the data according to some error metrics in different time frames, in different situations, and analyze the behavior of the model, which underlying error distribution it has, and so on. Using this knowledge, we can build the models more precisely, and we can also validate the model for certain purposes and situations.
When we want to employ the presented approach to data-driven sensor model validation at scale, we face a number of challenges that this project is specifically targeting through Gaia-X and the open decentralized data ecosystem developed in it. We require data in standardized formats and at defined and validated levels of quality meeting our needs. We also require standardized metadata to quickly locate this suitable data. And we require standardized usage rights to ensure that we can actually use the so located data. We then require the efficient exchange of said data, and given the scales of data needed, we want to employ ways of moving the computation to the data in a trusted manner. And finally, we want to automate this approach as much as possible across the many parties involved in acquiring, processing, validating, and using the data and the validation results. And we need to do this in a reliably traceable way to ensure transparency and credibility of the overall validation results. This is where Gaia-X as a whole and the open and decentralized data ecosystem developed as part of this project come into play. They provide tailored solutions to these problems. Many parts of this ecosystem are highlighted in the other talks today. There are, however, also some challenges inherent to data-driven sensor model validation that Gaia-X and the ecosystem cannot solve on their own. We need to define efficient and well-defined metrics that are acceptable to the industry for use in establishing credible model validation. To select the right validation criteria, we also need clearly defined requirements on the simulation for each particular use case derived from an overall system validation strategy. And to make the overall sensor model development more robust and sensor models more reusable, we need some form of standardization of sensor model capabilities and their validation across industry. There are currently already some efforts underway at ISO and other standardization bodies to address these needs, like a sensor model specific part of the ISO 11010 model classification standard series. Given that this is the halftime event of the project, let us recapitulate where we stand and give an outlook on next steps and expected future developments. We have defined relevant data formats and necessary metadata. We have also defined the overall validation concepts and methodology and performed a first implementation. We have collected a first set of real-world data using the formats and metadata and processed it for use in the project. We have also defined and calculated a set of initial metrics and KPIs and performed initial analysis. Going forward, we can also use the collected data to tune the sensor models against the actual observed sensor behavior derived from the measured data. As you can see, an initial tuning of a black box model against the observed data results in bounding box size determination that is much closer to the actual sensor than the out-of-the-box performance of a generic principles-based model from the OpenMSL. Comparing the model estimated bounding box in blue with the actual sensor data in white, we see that the generic model underestimates the sensor performance in terms of length determination, whereas the tuned model can approximate it more closely. The other area we are going to focus on going forward is the seamless integration into the Gaia-X environment, including automation and traceability. This will incorporate many of the ecosystem parts shown in other presentations today into one demonstration use case. And finally, of course, further refinement of metrics, KPIs, and validation methods will be needed to ensure practical usability of the proposed approach. Thank you very much from both Finn and me, as well as the numerous contributors to this presentation for your attention. We welcome any questions or comments you might have, either in the following Q&A session, or feel free to contact us and our project partners directly.